So good afternoon, everyone, wherever you are. We are going to start our second seminar from our series. I hope you had a good spring break and that you're all relaxed. It's a pleasure for us to introduce Dr. Alicia Palacios from Universidad Autónoma de Madrid, Spain. And a good thing is that we have managed to get a really substantial number of women talking in our seminars. And this shows that talent is present in many ways and in many forms. And we are really, really pleased. If you've been following, you see the amount of women who are taking part, really distinguished speakers who have been doing amazing work. So Dr. Palacios was born in Tomelloso, Spain in 1979, and she received the graduate degree in chemistry and PhD degree in 2006, both from the Universidad Autónoma de Madrid. And then she stayed at the University of Bordeaux. She held long-term postdoctoral fellowships in Lawrence Berkeley National Lab, California. And she's currently an assistant professor in Madrid, has published more than 75 papers, which is quite impressive. And she has been working on molecular physics, atomic physics, and especially on time-dependent treatments for the description of atoms and molecules, subject to ultra-short laser pulses. She has been awarded the Mildred Dresselhaus Junior Award. She's also currently the vice chair of the AMOPD of the European Physical Society. It's a pleasure to have her here, and she's going to continue a bit among the lines of what we have seen our previous week, in which she'll show you how one can really treat rigorously molecular physics and molecules interacting with very strong fields in very, very short timescales. So it's a pleasure to have her around. And now the word is with her, and she is going to talk about Attosecond time-resolved XUV-induced electron dynamics. So thanks for accepting the invitation, and thank you all for joining.
Okay, thank you. Good afternoon to everyone, or good morning to some of you. Thank you for the nicest introduction. I want to thank also the rest of the organizers for giving me the opportunity to contribute to this nice seminar series. I have also to congratulate you for having not so many women, but women, I mean, in the right percentage that it should be. So I congratulate you for that. And okay, this online format is not the real one, I have to say. It's not as enjoyable as talking to faces in our audience, I have to say. Although on the other hand, it gives the chance to reach a wider audience, which is always good too. So this is what we have by now. And today I'm going to start sharing my screen. As already announced, I will be talking today about Attosecond time-resolved XUV-induced electron dynamics. And okay, hope I managed to meet your expectations with this seminar. Basically, I'm going to focus the first part of the talk, or most of the talk, indeed, a large part of it, talking about our recent work on ultrafast charge migration phenomena in biomolecules. So I will start by reviewing the recent history of the experimental and theoretical achievements in the last year on this topic, and then I will present our theoretical data, in particular to describe an XUV pump, XUV probe experiment in glycine molecule. The second part, I will dedicate some time to illustrate what are the actual theoretical challenges nowadays in order to describe electron dynamics in the context of molecular photoionization. And to do so, I will illustrate it with examples using medium-sized and small targets, where we have more accurate methods. And we can see, and I will briefly discuss some of the current and forthcoming UVIR and UVB pump-proof schemes. So let me start by reviewing some history on the developments on ultrafast charge migrations in biomolecules in general and amino acids in particular. They're more intensive work in this kind of molecules. And the first experimental observation of charge transfer, as most of you already know, happened in the 90s, and it came by the hand of the group of Beinkauf and Schlack and collaborators. And this group, they were performing pump-proof schemes using nanosecond pulses, using as target isolated peptide change. And basically what they observe is that the chromophore of the molecule, so the site of the molecule that is absorbing the photon, was placed in the other end of the change where fragmentation was occurring. So therefore, in these works, they already discuss and predict the possible existence of some ultra-fast charge dynamics that was making the initial hole creating in this end to move along the molecule in order to allow the fragmentation in a different site. The first theoretical predictions on this soft femtosecond dynamics came by the hand of the group of Federbaum and collaborators. In these works, they were applying to gas phase molecules. This is one of the examples, glycine in particular, since I will be talking about this molecule. And in these works, they introduced indeed for the first time the concept of charge migration. And they introduced it in order to distinguish from charge transfer. Charge migration refers to the electron dynamics that is triggered and happens in just a few attoseconds or a sub-femtoseconds. In contrast with charge transfer that is usually associated to the charge distribution as the nuclei move away. So that they leads to the final fragments. So in these works, as you can see here, you can see, okay, they were exploring the sudden removal of an electron from a very well localized orbital. And what they observe is that after localizing the hole, this charge is migrating all over the backbone of the molecule in just a few femtoseconds. So this was the first time a theoretical approach was explaining this ultrafast process. The first experimental attempt in order to, sorry, I'm a bit disturbed with this box. The first experimental attempt on observing this ultrafast charge migration was produced in 2014, and it was performing the phenylalanine molecule. And basically the idea behind is that one comes with an attosecond pulse and ejects an electron, creating a wave packet in the ion. And the idea is that by coming with a delay infrared pulse, one ejects a second electron, and by looking at the ion yields of the decation fragments as a function of the time delay between the pulses, one is expected to gather some information about the dynamics in this cation. And an important piece of information here is that when they found these very fast oscillations in this yield as a function of the delay, they didn't show up in all the fragments, but only in some specific fragments, in these minor fragments with this ammonium dication. At that time, we employed as a theory the static exchange DFT approach, using a methodology I will explain later, developed by Pierre de Clève and collaborators, in which, in this case, we focus only in this part, just in the pumper dynamics. We were using just a fixed nuclear approximation. And then we were evaluating what are the electronic densities, how the electronic densities fluctuate over time. And the first thing you can observe in these densities, indeed, is that one doesn't get, when using an attosecond pulse, one doesn't get a very well delocalized hole, and in this case, but a quite delocalized hole all over the molecule. And this can be easily explained just when, by looking at the energetics of the problem. So I'm taking here just the example of glycine, the smallest amino acid, so it's a molecule. And here we have the different orbitals from which the electrons can be ejected. So we have here the ionization potential associated to ejecting an electron. In this case, correspond to the core orbitals, to the very inner orbitals of the molecule. As you can see, these are very high energies. So since we are interested in looking what happened with XUV pulses, that means we are going to be emitting electrons from this valence and inner valence orbital. Here we have a zoom. And if we come with a relatively long pulse, that means with a well-defined energy, it is possible to eject an electron from a specific orbital. And this can be captured in the photoelectron spectrum. So one can have a specific energies, and in this case, one could observe this kind of behavior. However, when one can with an attosecond pulse, they're associated to a very wide energy bandwidth. What happens is that the electrons can be ejected from different orbitals, and they're going to lay out in the same energy region. This implies that at these energies, what we are going to be creating is an actual electronic wave packet. And as a consequence, the resulting Hall densities are going to be quite delocalized all over the molecule. This electron density I'm showing here, it was computed with this static exchange DFT method. So let me just introduce very briefly what are these methods that we use in several previous works that some of you may know. So just in brief, the main theoretical challenge here is to deal actually with electronic continuum. So for the bound orbitals, they are computed by using DFT calculations, in particular using the ADF package. And for the continuum orbitals, we actually evaluated explicitly imposing the boundary condition of the scattering problem. And in this particular case, we use the Galerkin approach. Everything is well described in these references. But just as a small detail, since for the continuum, we want to have the electron escaping from the molecule, and we have to properly represent the long range behavior, we need to combine different bases. And let's say the Gaussian or even Slater type orbital basis sets that are very well localized, they are not any longer appropriate. And instead, we use, in this case, B-splines, which these are polynomial pieces that can cover the whole region. And then what we are using is a multicentric B-spline basis set, where we are combining one center expansion placed in the center of mass of the molecule, and this one center goes away up to 30 atomic units or 40 atomic units, depending on the problem we're exploring, or even larger, and combined with off centers expansions localized around the atomic centers in order to represent properly the Kato cusps. So in other words, in order to represent properly the bound part of the wave function. For the second part, if we want to look at the time evolution of the time-dependent wave function, we can just writing it as an expansion over these states. Just as a brief comment, and notice that in this implementation, in this particular one, the way this is written, the states are written as a single terminal orbital. So that means the picture remains within a single active electron picture. So if we want to look at the subsequent dynamics that are going to be associated with this cation, is mostly going to involve one whole cationic states. This is the method we were using in these initial works. For the time evolution of the n-electronic wave function, then we have to define the reduced density matrix in order to be able to define the electron density for the n-1 electron system. And what we usually plot is not so much electron density, but the whole density as it was proposed in previous works. So now, by applying this methodology, this is what we obtain. And as you can see, even in this well-delocalized distribution, there's still fluctuations occurring in the sub-femtosecond regime. And this is what would be a realistic wave packet interacting, induced by an attosecond pulse. And I just want to point out that these two pictures are indeed not in conflict at all. I mean, on the left, what we are seeing are the initial wave packet created with an attosecond pulse in glycine. On the right, what we are seeing is just the effect of having a sudden removal of a specific orbital. And this can be done with any artificially created pulse or any other source, but these are compatible pictures. We are just starting from different initial states. Indeed, in order to check our first implementation some years ago, the first thing we did was trying to reproduce this behavior. And we actually took the 11A prime orbital from the neutral. In that case, one has to be careful what we define as electron correlation, because the electron correlation that is observed here is that one of the ground state of the neutral. So if one represents the ground state of the neutral, and in this case we just took, as they did in this word, a Hartree-Fock orbital for the 11A prime, and then we take this orbital and we just simply project it into our one-hole cationic states, then what we obtain is the exact same result. So we can see here the direct comparison, and the effect indeed can be perfectly explained just by a superposition of one-hole cationic states. So these pictures are totally compatible. It's just a question of what do we set up as an initial wave packet. And over the years, I mean, I just pick some recent references, but there are a ton of references here. So if someone feels missed, I'm sorry. But there are many experimental works that have been done later, also in small molecules, trying to track this ultrafast charge migration using HS high harmonic spectroscopy techniques, for instance. There are other works, other theoretical works, for instance, in this one by Brunner et al., where the initial wave packet is created, in this case, by coming with an X-ray, one ejects a core electron, then an Auger-Meitner decay occurs, and then one creates an initial wave packet of the valence states after this process. So this is a different way of getting an initial wave packet, and in this scenario, an ultra-fast transmigration is also observed. So these are just some examples. There has been also experiments in other amino acids like tryptophan, where these femtosecond fluctuations were also captured using UV, IR, PAM-prof schemes. So the question is, what are the open questions nowadays? What are the drive of this field right now? And one of the main questions that are still to be solved or to be fully understood is how it's possible that electronic coherences survive long enough to be probed when the nuclear degrees of freedom comes into play. And for this, this is just a list, again, this is just a short list of the many works that are nowadays being performed in order to understand and to grasp what is the role of the nuclear degrees of freedom in these processes. And basically one has to take into account two different aspects of the same coin, which is, in one hand, introduce the nuclear motion effects by the fact that the initial distribution of the ground state that we have, but also once we have ionized, then the ionized molecule, the nuclei can also move. And in this case, when nuclei come into play and this nuclear motion is playing, then non-adiabatic couplings may have importance and may be relevant. And therefore, for that particular description, then one will need a multi-reference method in order to represent the electron nuclear motion coupled in the cation. And for this reason, I'm going to show now the standard method of our static exchange DFT, but using a multi-reference approach. And other main question is why these electronic coherences are only captured in a specific fermentation channel. As we have seen in the experiments, it doesn't show up in every fragment, but only in specific fragments. So this kind of indicates that there must be some prof selectivity in the prof step. So these 2 points are the ones that I'm going to try to address with our recent data. So the first thing, what we use now is a multi-reference static exchange DFT. So our n-electron wave functions is still written as an antisymmetrized product of n-1 electron wave function and the continuum electron wave function. This wave function is still obtained evaluating within the static exchange DFT level. However, now the full wave function is treated in a multi-reference way. Okay, so the big advantage of using still this approach is that even writing this function as a multi-determinant form, the final dipole couplings that represent the coupling between the ground and the final states that are going to give us the photoionization amplitudes, they can still be reduced to single particle matrix elements, therefore simplifying a lot of the work. This implementation was developed also with Piero De Cleva in collaboration with Aurora Ponzi, so all the details can be found here. And in the particular results I'm going to be showing today, both the neutral and the cation has been obtained for the electronic structure using a restrictive active space circumsystem field approach. And we are using the one hole, one particle states, but we also include further excitations, including up to 2 hole, 1 particle and 3 hole, 2 particle configurations in our basis. So in this approach, we are going beyond the one hole states approximation that we use in previous works. And the first thing, of course, is to compare what I'm going to call from now on the CONSAM DFT approach that I explained before, in contrast with the results of this multi-reference DFT approach that we are using here. What I'm showing here is the photoelectron spectrum of glycine, in this particular case obtained with monochromatic light at 40 dBs. We took this because these are the only available experimental data that we can compare with. And we can see that indeed the difference between the CONSAM and the multi-reference is not so big. We have some features now that are better represented. So let's say this multi-reference approach is doing a slightly better job for some states. What I'm showing here are the actual cross sections for the different orbitals as a function of the photon energy. If we compare these two graphs, we can see already that the CONSAM static exchange DFT was already doing quite a good job. So somehow saying that most of the dynamics can be in a large extent explained just with the one hole states for the first ionization step. And a second ingredient that we are going to be including now is again the interaction with a realistic attosecond pulse. And the third important ingredient, as I announced before, is to include the initial state distribution. So we include the nuclear degrees of freedom for the initial distribution of the ground state. And for that, we just use a standard Wigner distribution that has been used in several previous works in photochemistry. What I'm showing here are the ionization probabilities for a 16 eV pulse of obturations of 3.5 femtosecond. This blue shadow corresponds to the energy distribution of the pulse. And these lines correspond to the initial probabilities, so the populations of the different cationic states in glycine molecule. And I want to recall here that we have 3 important ingredients. The scattering states actually evaluated, the initial state distribution, and also the pulse interaction. And these ingredients makes an important difference if we, for instance, compare what will be the result of the spectral intensities that one will obtain if one just ignore the electron in the continuum, so the actual evaluation of the electron continuum wave function. So these are the square Dyson norms from the neutral to the cation. And as you can see, these main lines correspond to the one hole states. These small lines are the so-called satellite states, which correspond to further excitation upon ionization. And what we see here, if we compare these lines, is that the resulting probabilities, ionization probabilities for each cationic state is something more than just the Dyson norms convoluted by the pulse, but the explicit evaluation of the continuum is necessary and have a real impact here. So what we explore here are the different probabilities if we use different pulses. In this particular case, we have kept the pulse duration to 3.5 femtoseconds, and we just move the central frequency of the pulse. We can see very different distributions. And in case you're wondering why this relative weight between the states are changing, remember our cross sections that as a function of the photon energy, mainly in this low photon energy region, there were important changes as a function of photon energy. So this is what is making this probability variation. Of course, we can now look at the whole densities as a function of time for the 3 different pulses. And in every case, we found sub-femtosecond oscillations in the whole densities created. Of course, these are the results of the different superposition of states, of cationic states that we have here. So yeah, let me recall, if we want to now introduce nuclear motion in the cation, so what happens after we trigger this wave packet, we create this electronic wave packet, what will happen when this couple electron nuclear dynamics come into play in the cation. And in order to represent this, what we are using is a surface hopping approach. Is based on the tallest surface hopping formalism. In this particular case, we're using an implementation developed by Jesus González Vázquez in our group. It's a homemade implementation of that. And we can see here the result of the adiabatic population for each cationic states. We are only plotting those ones that are significantly non-zero for each of the 3 pulses here. If we look at the time 0, these populations, of course, correspond to these populations plotted here, right at the end of the pulse. And then when we let, by means of using the surface hopping, in which we combine the quantum electron simulations for each step, and for the nuclei moving classically, just following the classical equations of motion. And by combining these expressions, this is what we found. In this case, we have run up to 100 trajectories within our Big distribution. And we can see, for instance, that in the case of the 12 eV pulse, the non-adiabatic couplings are not making a big deal. Indeed, all the states remain with, over time, with almost constant populations. In the case of the 16 eV pulse, however, we see that the non-adiabatic couplings are really making already some differences up to around 5 to 6 femtoseconds. So there's some exchange of populations among them. Same thing around 20. We see one of the states, the second state remains on almost constant in the populations, and the others are changing. So the main question now here is that, okay, how this translates into if we want to probe these dynamics, how this translates into our observables. And the first thing we have to see is that, of course, if we keep these almost constant populations of these states, one could see a coherence between those states long-lasting, as long as the reaction path that is explored, so the surface, the potential surfaces that are explored in these states remains within the same limits. Another way of looking at this and trying to understand this is, let's look at how the actual geometries of the molecule are evolving in time for the different states. And this is what is plotted here for all the trajectories. So on the left, we see how the CN distance is varying on time for each trajectory. And these color bars are indicating the state in which you sit in the trajectory. So we can already see that these trajectories that are associated to states, to relatively high states, are the ones that have a tendency to dissociate along this bond, whereas on the right we have the same analysis, but now looking at the stretching of the CC distance as a function of time, and we see now clearly that are, however, the lower cationic states, the ones that have a tendency to break along the CC bond. So these results are already telling us that by the creation of a wave packet with different states are driving us to different fragmentation channels. And we can take advantage of this in order to measure the electronic coherences. Indeed, this could explain why some coherences only show up in specific fragments. And in order to test this, the final ingredient that we have to add is the probe step. So what we are going to do now is looking at the dication final fragments for each delay between the palm and the probe. So in this case, I'm showing as an example one of the trajectories. This particular case corresponds to one of the lowest cationic states. So you remember there were those that were breaking through the CC bond. And then we take at each specific time, we come with a probe pulse, and then the molecule then gets further ionized. And then what we are going to do after the action of the probe is waiting an extra 45 femtoseconds. With this time, we basically ensure that we are reaching almost an asymptotic region. In other words, if we look at an experiment, the experiments are going to measure the cation fragments at infinite times. So we need to wait long enough after the probe to see what is the fragmentation path that is taken. So we now take in the cation a different delay, and we just scan with the probe, wait another 45 femtoseconds, and look at what does the cation fragments, and so on and so on. So we really perform different, an actual scan in time delays for the evolution of the cation. So these are the dication fragments after a long enough time. But of course, in order to decide if these fragments, these are pictures, so I can just stop plotting the bond and then the bond is not there. But one has to find a criteria in order to decide in which moment this molecule is really going apart, or in other words, when the charge has redistributed enough and then the fragments go to the asymptotic limit, to the final channel. And a way of doing it that is very common in chemistry is just by evaluating the charge around the different fragments. And here it's clear that there's a breaking through the CC bond. And if you realize before, even when the cation form was still up to 10 and 15 femtoseconds stop bonded, when the probe comes and ejects the second electron, we see that even in a very short delays, we are seeing these fragments through the dication breaking through the CC bond. So now what we take is another trajectory. Let's take now a trajectory associated to the highest cationic states. Those were that we saw that in the long times were breaking through the CN bond. And then we perform the same probe scheme and then look at the dication fragments as a function of the delay. And again, we see in this case, we still have some oscillations in the charge until we reach the limit in which we see that the charges are very well distributed and then the dication is breaking through the CN bond. And of course, we can do the same analysis for those trajectories that is not clear where is the bond that is stretching, because of course there's an important part of the probability that goes into the cation in the non-dissociative form, the cation, so the bound states of the cation. So these results, what are indicating is that by measuring specific fragments in the cation, one can selectively probe the coherences between a few electronic states in the pumped Weypacker. Okay, so in other words, looking at our results, basically the low cationic states involved in our Weypacket are mostly probed into this channel breaking through the CC bond, whereas the Weypackets formed with the higher cationic states are mostly probed into the dication fragments that are breaking through the CN bond. So as a summary, up to now we have seen, in order to reproduce these complex molecular dynamics, we had to use many different and combine different methods. In the first case, in the first place, we need to properly represent the scattering states in order to get realistic initiation probabilities and initial Weypackets. We need to take into account the pulse parameters since there's a high dependence on them. We also need to look at the initial state distributions. And if we want to look at the coupled electron nuclear dynamics, we have to find a way of coupling. And for these large molecules, the only option is to do a semicalcical approach. And in this case, we were using this surface hopping approach. And finally, we can then include the probe step and using also the same approach, try to see what are the fragmentation of the dication. So the question now is what is next? And we are working now in this direction, which is looking at the coincident photoelectron spectrum. Since we have seen here, it is important to measure not only electrons, but also the coincidence with the different cationic fragments. It would be nice to have this observable. And we did the first approaches looking at the photoelectron spectrum. In this particular case, we took the example for the 16 eV pulse. Remember, these are the initial cationic states, the initial Weypacket that we create, and we came with an XUV probe. And in this case, what we measure is the photoelectron energy as a function of the time delay. These results correspond to the fixed nuclear approximation, where we see we can get very nicely the electronic beatings corresponding to this Weypacket. If we now include the initial Weypacket distribution, we see that many of these coherences are partially washed out, as it would be expected. But still, if we can see still this behavior, and if we do a Fourier analysis of this data, we still can see and distinguish this oscillation. So the next step will be to get the full coincidence photoelectron spectrum. And as future perspective, we are also working, and as long as many other groups in this field, in trying to get new strategies in order to probe this ultrafast phenomenon. In particular, there are XUV, X-ray, X-ray, and XUV-IR experiments running right now. And the next theoretical challenge also, in particular, if we want to represent this kind of approaches with the infrared field, is to evaluate not only the boundary continuum states couplings, but also the couplings between continuum and continuum states. And this is not implemented in all the methods. So in order to illustrate what are these channels, as I was saying in the introduction, I'm going to pass now and try to illustrate these bottlenecks that we are finding in the theoretical methodologies in medium size and small molecules. And let me separate first of what I'm going to call medium-sized molecules are diatomics or small polyatomic molecules, as these ones shown here. And to represent these molecules, as we saw for biomolecules, nowadays there are a plethora of quantum chemistry packages that are able to provide very good representation of the bound states. We can use from DFT-based methods to post-Hartree-Fock methods. This is just a collection. I'm missing many of them. But again, if we are looking at photoionization problems, if we want to look at what is the XUV-induced dynamics, there's a high probability that we are going to have one electron ejected. Or if we want to probe it, we need to evaluate explicitly the electronic continuum. And for that, there are less methodologies available, although there are many under development. Again, we can classify them as those using DFT-based methods for the N-1 electron fashion, or post-Hartree-Fock methods. In this case, we have XChem, PolySCAT, and R matrix. And what is more scarce are those methodologies able to represent continuum couplings. There's only a few words using R matrix or this static exchange DFT approach. And let me just show an example on why these continuum couplings are necessary every time that we want to represent a UV-IR Pamplov scheme. I'm gonna just show a very brief example using the CF4 molecule. In this case, we come with an attosecond pulse, but now the probe pulse is not gonna be a second XUV, but an infrared field. And in this case, we are not ejecting a second electron, but the infrared field further ionize, is absorbed already in the continuum. So that means what it's gonna do is interacting with electron in the continuum and leading to the same final states. In other words, the final states that we are analyzing are those ones that contain the same information or in the same energy region that the pump probe is acting. What I'm plotting here are the whole densities associated to CF4 that are induced by an attosecond pulse. We can see here also these charge fluctuations. And the interesting part is to extract the photoelectron spectrum that in these polyatomic molecules is visible. And in order to see what is happening here, we are seeing some fringes. I'm plotting here the spectra corresponding to the different valence orbitals. And we see in all of them that in the region where both the attosecond pulse and the infrared field overlap, which is in this inner region, we have a more complex patterns arising. But interestingly, when both pulses are not overlap any longer, there's still some fringes for longer and longer delays. So these are telling us, since at these delays, the electron is expected to already be far away of the molecule, this implies that the infrared field is doing something more related to the cation behind. So what we are seeing here in red, we have the profile of the infrared field. And as you can see, if we look at these fringes, these have very fast oscillations that can be related to transition between electronic states. And indeed, we did a very simple model to demonstrate that this fluctuation fit with the interference between the one photon absorption. Since we have a very wide bandwidth, again, we can emit electrons from different cells. And when the infrared field comes, it is possible to have a second transition filling up this hole. So what we are seeing in this spectra are nothing else but interference between the one photon absorption and the one photon followed by a two photon IR absorption. And this interferometry gives us the information about the dynamics that is triggered by the pump. In order to represent this problem, it's necessary thus to have the continuum couplings between the states, otherwise it's not possible. And the open theoretical challenges for polyatomic molecules nowadays is mostly to introduce in this quantum theory the electron nuclear motion. Again, there are some available tools in order to introduce in a semi-classical way, as we have seen in the large molecules, but quantum treatment for the nucleus is still not possible, but for very small molecules like nitrogen. And just an illustration or trying to convince you a bit why, instead of going to very, very big molecules, it's also interesting to keep focus on very small targets, is the fact that for here we have full dimensional methodologies. That means by just applying theoretical methods, one can design new strategies. So let me give you some examples when theory comes first. This is an example in A2. It's very similar to what we were doing in glycine indeed. So we come with a pump pulse and create a wave packet. In this case, instead of creating it just in the ion, we are creating in the excited molecule. The wave packet moves, and then the probe comes and ejects the electron. And the idea is that by looking at the ionization yields as a function of the delay between these two, one is expected to be able to trace the dynamics of this wave packet. In order to make a feasible approach from the experimental point of view, we are using two identical pulses, two identical attosecond pulses with a delay among them. However, when one uses two identical pulses, what is going to happen is that on top of this sequential excitation and ionization process in the pump probe scheme, we are also going to have that the pump is creating this wave packet, but by two photon absorption of the pump itself, we can also further ionize, and we are also creating a wave packet here. That means that when the probe pulse comes, as we saw before through the sequential process, is also creating first a replica from the ground state, because we are replicating this step. So we are going to see an interference here, and this interference here is also going to be mixed with interference induced through the sequential process. That means, but far from this being a problem, the nice thing is that this interferometry can be used to get even more information of this wave packet. And this is what we did in this work some time ago, what we call this molecular interferometer. And if we use if we look at just the total ionization yield, so not energy differential, just total integrated, as a function of the delay, one sees very fast oscillations corresponding, of course, to electronic beatings. And on top of that, we have a slower oscillation that correspond to the vibrational components, to the vibronic components in these states. Indeed, if we do just a short time window Fourier analysis, similar to that performing frog analysis for experiments, we can look at the different components in energy as a function of the delay. And what we see is in the energy resolve, we have these two components corresponding to the first and the second excited state, so we can identify the electronic states that are playing a role. While when we look at the information in time, what we are seeing here is for each wave packet, for instance, we are seeing here the nuclear revivals of the bound states associated to the first excited state, as well as the nuclear dynamics associated to the second excited state. So we can get, and we can fully reconstruct this wave packet. Indeed, in parallel to this work, the first experimental attempt doing an XUV pump XUV probe in the hydrogen molecule was performed in the group of Dimitris Haralambiris, and they could find this identification of states. In this case, they couldn't do the full retrieval of the wave packet because there was not a CP stabilization, which is a requirement, good coherence between the pulses in order to see this very fine interferometry. More recently, we have kept with this work, and instead of looking just at the fully integrated yields, one can also look, as we were discussing before, on the coincidence measurements. And in this case, we are looking at total final energies as a function of time. So this is the total energy of the fragments, and both ions and electrons. And we can see here the very fast oscillations. If we now perform again a Fourier transform of this signal, this is what we obtain. So this is an analysis in energy and total energy encoded in these oscillations. And okay, all these signatures have encodes different information, but I'm going to focus just in this region. If we highlight this signature with components between the 10 and 15 EVs, if you remember, these are the energies where the excited states appear. What we are seeing here is the clear signature of the first excited state with a vibrational progression and the second excited state with a vibrational progression. And this signal is really being captured directly in the yields. And for comparison, what we are showing here are the actual excitation probabilities and that are obtained just by the pump pulse. And we can see here the perfect correspondence between the vibrational progression in these two lowest excited states. So in other words, one can perfectly reconstruct the full molecular wave packet by just analyzing the energy differential ionization signal in the cation. Among the strategies to access electronuclear dynamics, we can use pan-prof schemes, but we can also use other schemes like one color, two photon ionization. So this is just an example also in A2. The approach is similar, but we are just using a single pulse. And in this case, instead of playing with pan-prof with different pulses, one can play just with the laser parameters. In particular, one can take a specific pulse duration. And if we do a scan in energies, as is nowadays feasible in several facilities, one can see that one can control and manipulate the outcome of the reaction. And indeed, one can manage to control the different ratio between the dissociative and the non-dissociative yields. And this is what is shown here. And indeed, there was years after this work was performed, there was an experiment conducted by Daniel Duweck and collaborators at Fermi. And using Fermi, they could exactly reproduce this behavior with 50 femtosecond ondulation pulses. The availability of free electron lasers nowadays give us the possibility of studying many nonlinear processes that were not possible due to the low brilliance of previous laser sources. And now all these problems are now to be explored. Not only in molecules, but even in atoms, there's still a lot of things to learn. For instance, about the electron correlation. This is just an example of helium. This is again a two-photon process that has been inaccessible for years. And now with the free electron lasers, it is possible to access this. In this case, I'm just doing probabilities, two photon ionization probabilities as a function of photon energy. And the idea here is that by looking at the fully differential yields, that is to say the angular distributions of the electrons, one can also get information about the correlation of the ground state and the intermediate states that we have here. And if we look even at some very, very, very tiny features, that this one appear at these energies, what we see here are the typical Fano profiles associated to auto-ionization occurring after two photon absorption. And this what can be nowadays energy resolved in experiments. These are just theoretical data, but we can see that as we do an energy resolve study and we look at the different partial waves, we can see that at the specific energies, the electron is ejected, almost forgetting completely what was the light direction. And this is just due that is sitting long enough in this auto-ionizing state before decaying. And all these things are now accessible thanks to the developments in the new laser technologies. And just to summarize, I want to finish here. I'm taking a bit too long time. Just to summarize what are the perspectives on these studies on ultra-fast electron dynamics. If we are talking about biomolecules, there's still a lot of work trying to understand why these electronic coherences survive, if they survive, in which species they are. We are studying now new molecules, aminophenol, paranitroanilin. We are studying the pulse shape effects. There's a lot of field here and a lot of room trying to understand and try to set up a realistic attochemistry area or even attobiology. I mean, can we manipulate at the attosecond level the electronic dynamics in order to observe a macroscopic effect into the final fragments, into the chemistry properties themselves? There's a lot of work in trying to design probing strategies and what are the actual most suitable observables. And at least from our first approaches, I hope I convince you that a time-resolved electron ion detection would be desirable. And also in order to obtain time-resolved images, not only of deionized biomolecules, but also of excited biomolecules, there are other schemes that are being applied nowadays. In the case of small polyatomics, the big challenges are, as I said, including the coupling with nuclear motion, and there are many experiments right now using, for instance, attosecond electron streaking or rapid techniques in order to, for instance, try to understand if the so-called photonization time delays that has been widely explored in atoms can be exported to molecules, and what will be the interpretation when nuclei and electrons are simultaneously coupled. And for the case of very small molecules and very small targets, I'm pretty convinced we should be still using them as testbed targets to design the novel approaches. I think I have shown you enough data to convince you on the complexity of just electron nuclear correlation dynamics. And already even in these targets, it's not so straightforward. And there's some forthcoming Attosecond XUV, and soft X-ray experiments. We have been also working, trying to induce for these experiments with very high energies, non-dipole terms that come into play. And also the fact of using angularly resolved ionization yields as an observable with the electron correlation fingerprint is exposed there. And just to finish, let me give the credit to many of the people involved in the projects I have been showing today. I have highlighted with pictures the people involved in the studying ultrafast charge migration in biomolecules, 2 PhD students, Jorge Delgado and Manuel Arestiaso. He's already gone. Jorge is still working in the group. Jesus González Vázquez, who is a real quantum chemistry expert, I have to say, and he's the one introducing the surface hopping approaches in the group. And for sure, Fernando Martín, who is leading many of these works, and the valuable collaboration of Piero de Cleva with the static exchange EFT approaches. And then just quickly, this is Preciat, González Castrillo, 2 postdocs working in these 2 different topics, and the people involved in the atoms, in particular the postdoc Diego Bol, that was in my group for 3 years. And nothing else, but thank you for your attention. I hope you are all still there, and I will be very happy to take questions now.
Yeah, so thank you very much for your great talk, Alicia. There is one question in the Q&A. Just a reminder for everybody, if you would like to ask questions, please raise your hands or type your questions directly in the Q&A section. So the first question is from Elke Fasshauer. How do the continuum couplings affect your time-resolved spectra? In which situations are they especially important to include?
Okay, continuum couplings are going to be important depending on the light sources that you are using. Meaning, if I'm looking at for instance, the first problem with the PAM probe, I go to the cation, and from the cation I go to the dication. Of course, in this case, the continuum, I can escape somehow, and I can use approximation and avoid these couplings. But for instance, if I'm using any XUV-IR approach, let's say rapid techniques, in the rapid techniques you come with an attosecond pulse train, and precisely the continuum couplings is what makes possible the transitions into creating sidebands between them. Okay, so I come with a train, and I have the fingerprint of my comb in energy, and then if I come with an infrared field, I just induce transition between different sidebands, and the interference between the sidebands are the ones responsible, are the ones carrying the information of the dynamics of these states. So here, if I don't have continuum couplings, I cannot even solve the problem, because this is really the infrared field is coupling the continuum. This is the second example I gave in the CF4 molecule. I can share quickly. So in the CF4 molecule, for instance, this photoelectron spectrum is the result of really introducing the continuum couplings. If I don't have these couplings, I wouldn't see anything. I will just see basically whatever is happening from the ground to the XUV pods. I wouldn't see any structures or anything, because really the infrared field in this case is really, let's say, the electron in the continuum is the one that is absorbing the momentum from the photon. So it depends on the specific problem you are studying, for sure. I mean, it depends. I don't know if this clarifies well your question.
So are there further questions? Is the reply okay? One thing that I would really like to ask and got me curious is about the coherence, because you have shown a plot in which you had only electronic degrees of freedom and you froze the nuclei, and then you had another situation in which the nuclear degrees of freedom were included, and all those phase relations, they were gone. You got rid of most of the patterns. So my question would be, can you quantify the coherence? Because from what I understood from your talk, this is your enemy, right? Can you quantify?
I mean, I was tempted not to show this photoelectron spectrum because I think it mislead to the people. What I'm showing here, I guess you refer to this one. No? Okay.
Yes, sorry, I was muted. Exactly. Yes, I refer to that one.
This is the photoelectron spectrum. That means we are counting here every electron coming from every fragment, everything. So all electrons are counted here, okay? And if I look at it as a function of the delay, of course, if I am in the fixed nuclear approximation, where everything is frozen, I can see every perfectly well-defined the energy gaps. What I'm seeing here is nothing else but the beatings that when I come with a probe, I probe this into a final state. Since I have a short pulse, all these guys come together into the same final states and they interfere. And that's why I can see these beatings, okay? These beatings are given by the energy gaps between the cationic states involved in the wave packet, okay? What happened is that in this case, I'm assuming the cleaving distance. If now I don't have just a single one, but I have a distribution, an initial distribution in the nuclei for different geometries, what is going to happen is that these guys are not exactly placed at the same energies, no? But there's a surface potential there, okay? That depends on the geometries. That means if now I do the same thing and I just gather all electrons, I get this. I have to say that these are not washed out. I don't know if they are visible in the screen, but we can see here for these energies, we can still see the oscillations. Of course, they are way softened because they are partially washed out, but there are still important variations. Indeed, if you do the Fourier transform of this, you still see very nice oscillation. Not with the same amplitude as here, but you still are visible. But the important part here is that what I'm plotting here is the worst thing I can plot, which is all the electrons coming out. Remember when I was saying, even in the experiments, they never capture off the electrons, quite the opposite. They look at the ion yields of specific fragments. In that photoelectron spectrum, I'm adding the electrons from this fragment, from all possible fragments, all together, okay? That's why it's even more obscure. But if now I separate the fragments and I just take each individual fragments, then I'm back into this situation, okay? The main question here is like, if you want to do an actual experiment and capture all the fragments, that's why the conclusion would be, the idea would be to measure the electrons that are associated to a specific ionic fragments. So an ion-electron coincident detention as a function of the delay. And then you can reproduce that. Then you are back in the previous case. So how to say, this is the worst scenario. Let's say I'm putting the worst observable that we could choose, you could choose, which is just taking all the electrons, irrespective of the ion that is left behind. Okay, did that clarify the point?
Yes, thank you so much. Because I mean, then the message would be that there's still something left, even when you have so many electrons, and this is amazing.
Yeah, the difficult thing is, I mean, the thing is, okay, you have the wave packet with everything, and if you just measure all together and you select, then everything is blurry. So the question is, can we cleverly choose the probe as we have seen when looking at, for instance, specific fragments, but instead of getting everything, you are just probing specific parts of the wave packet. So instead of getting all the states that were there involved, I'm going to be capturing the electronic coherences only between a few states, those that are follow the same reaction paths. And this is what you are going to capture if you do a probe by looking at the different fragments. So this is really the worst scenario.
Okay, thank you. One question we have from Nana List. What are the possibilities for creating electronic wave packets in neutral molecules?
Okay, neutral, you mean in excited, no? I mean, you mean like in photochemistry, usually one comes with optical pulses, and these optical pulses are usually in the femtosecond region, so they are very long. And in photochemistry, the common thing is one is looking at the evolution for a single state. I guess your question is, how can I create a wave packet there? Okay, in the same way. I mean, what I showed you here, for instance, in this this example in A2, this is this is excitation of the neutral. Oh, sorry, I'm rather. Okay. This is in this scheme that I was showing here. What we are looking is with the pump, we excite, and then this evolves in the excited molecule. And then with the probe, with the delayed probe, is when we ionize. And then we look at the ionization, but to get information on this. In this wave packet that we're reconstructing here, this is the excited. So this is the neutral molecule dynamics, what we are reconstructing. And the first experiment was already performed here. And in this experiment, they could identify perfectly the contributions from which states were there. They couldn't reproduce the full wave packet, as I said, because missing coherence in the generated pulses, attosecond pulses. But this is already experiments being performed in this direction. So it is totally possible. The only thing is that, of course, you have to go to energies down there, and the difficulty if you go to large molecule is that usually the excitation energies are between 3, 4, 8 EVs, and having attosecond pulses in those frequencies is quite a challenge. But still, I mean, when you hit with a short pulse, the non-adiabatic couplings sometimes play a role, and you're generating their wave packet. So it is possible. So
another question from Kalyani Chordia is, could you please discuss the different fragmentation observed for glycine, where OH was fragmented for tau equal to femtoseconds and later only for NH2 plus and the rest?
Where OH was fragmented for tau 2, okay, I guess what? I'm not sure I understand the question.
Yeah, could you please explain?
Can they open the mic?
Yeah, you can raise your hand quickly if you would like to.
I'm not sure.
But because you had
fragmented
glycine at different times, and then later you had just the rest. I don't.
Okay, I see what you mean. Okay, but this is an illustration. That's precisely what I said before, that this is an illustration. I mean, I just can't put here a bond or not. This is a question of the way of the, I understand now the question. Okay, this is an illustration that comes out from the program of the DRAW program. And the DRAW program just set up kind of a minimum wavelength for which the program puts an actual stick or not, okay? But this draw or this plot is not a consequence of the charges. That's why when we want to look at this, this is for visual purposes. But if we want to see if there's actual a real fragmentation or not, that's why we do this charge analysis. Here is clear, okay? In order to see if there's really fragmenting, we look at if we just calculate the charge around this fragment and around this fragment in this case, and then we look at the charges. And the fact that here we have 1 and 1 is already telling you that it's really well separated. Or in this case, for instance, it takes a while. So we see that here there's still some distributed charges. So at these delays, it's not clear that the fragments have fully gone apart. Okay, but here they do. So this is just an illustration, if that was your question. So the way of looking at it, and this is done in chemistry in other, for instance, also in fragmentation of excited states, you usually want to calculate the electron densities around the charges in order to decide if this bond is already broken or not. So this is more of a picture more than a reality. So I hope I understand.
Yeah, thank you. There's another question from an analyst as well. To what extent does the ionization process affect ensuing cationic dynamics other than the initial wave packet? Has this been studied in diatomics?
To what extent does ionization process affect the ensuing cationic dynamics? Well, I don't get the question. I mean, the ionization process, the ionization process is the one that where you have a cation. Can you open the micro and explain a bit more? I really don't get the question.
Yes, feel free to join. So if you would raise your hand, we can discuss this live. I think it's thank you. We appreciate it. So please unmute. And
can you hear me?
Yeah, now yes.
Yeah, we can.
Yeah, I was just wondering the actual process itself as the electron is leaving. So I guess that is not part of the, whenever you show the cationic dynamics, that is sort of after the electron left.
Yep.
And I was just curious about sort of as the process happens, and I imagine that that is something you have included in the smallest examples that you presented, but I was just curious if you have compared to without.
No, we did, and this is a very good question. I don't have the slide. Do I? I thought I have this supporting slide. This is indeed a very good question. Maybe I can show it to you quickly. Oh, I don't have it here, but indeed we publish these results. I mean, they're published. So if you look at our literature, in one of our last papers in glycine and phenylalanine, we compare indeed in glycine exactly what you are saying, because for instance, the electron densities we are plotting there, as you very well said, is after we integrated, and then we are looking at the n-1. So we are focusing in the cation. But you can look at the electron densities taking into account the n electron, so the leaving electron. And what we saw is that after 200 attoseconds, 300 attoseconds, the electron that is leaving doesn't have any further influence in the cation dynamics. But it is a very good question. I mean, if you look at right after the end of the pulse, you look at the actual electron density, accounting for the electron that is leaving, the electron density that is slightly different, okay? Because the electron is still interacting in the molecular potential. And if you look at these electron densities as a function of time, you can see that, and you compare the case in which you ignore, you say, okay, the electron is gone, versus the case where you have the electron in, you see that in the first 200 attoseconds, there's a slight difference, but then it goes away. I mean, it really, after 200-300 attoseconds, the electron that is leaving can be safely forgotten. Indeed, this is the approach that most of the works from most of the people that you saw listed there, everyone already ignored it, but it's true that it was good to check it, and we did check it. It would be nice if I was able to show you a figure that you will see in a second what I mean. No, but okay, I don't have it here. Yeah, no, I don't have it here. Yeah, sorry, but I hope I could I answer your question. Did I?
Yes, thanks a lot.
Sure.
Sorry, I'm muted. Thank you so much for asking the question. Are there further questions? Are there further comments? Is there anything someone would like to ask? we are going to start the live stream. We are going to stop the live streaming soon. So also, if you would like us to remove the questions afterwards, drop us an email. And there's a further one from Kalyani Chordia. Does the symmetry of the molecule change with onset of nuclear dynamics, and does that affect the electronic structure of the molecule? Could you please talk more about this?
Yeah, it will. I mean, I didn't show anything here in that regard because, I mean, glycine doesn't have any symmetry. Yeah, so the molecule I was talking about, you don't have any symmetry imposed there. So there was not a regard on that. But I mean, but of course, if you are, for instance, in CF4, if you start by the molecule and then you see fragmentation, for instance, on a specific bond, then of course you are changing, let's say, from the symmetry of the molecule. You could be from TD at tetrahedral, so you will be to a 3,3 C3 symmetry. So yes, I mean, it will affect, but not in the regard of the description of the problem itself. It's just changing the, okay, you're changing the symmetry of your target. It will affect in the measurement. I mean, depending on what you are measuring, you have to take this into account. I mean, I'm not sure if you are thinking in a particular case with this comment, because of course the molecule change symmetry as, I mean, glycine is not the case because there's no symmetry, but very highly symmetric molecules where they fragment, of course, they change symmetry. So they have an impact, for instance, when you compute in a quantum chemistry package, you usually define the symmetry states from the beginning. But I am not sure if you were thinking of something specific on that, some specific problem or... so if you want to open your micro.
Yeah, if you would like to unmute yourself, feel free to join. Please unmute and we can continue the discussion.
Hi, can you hear me?
Yes, yes.
Hi. In the recent experiments, mostly they align the molecules to study the quantum chemistry or light matter interaction. So in this case, when we use like near IR pulse or terahertz pulse, in this case, the nuclear dynamics, I mean, it will affect the nuclear dynamics. And then afterwards, when we study shorter pulse, we are actually considering, like in calculation, the ground state without any modification in the nuclear structure of the molecule. But in reality, do you think that with the use of alignment pulse, this will change? And then we should also consider these in the calculation?
Yeah, I mean, this is important. I mean, this is very important. I mean, how, let's say, how the light interacts with the molecule. Let's say if, for instance, I mean, in glycine I didn't give the details, but for instance, when you do the simulation, of course, you have to see how is the light polarization. If you are in dipole approximation, you care only on the polarization vector with respect to the actual molecule. I mean, let's say, I mean, you have to compute the interaction in the different axes. So this is very important, and the resulting amplitudes are very different. I mean, this is very obvious if you think of a diatomic. I mean, coming with a light like this or coming with a light like this is not the same at all. And indeed, if you took hydrogen molecule, if you come with a light perpendicular to the molecule, the ionization yields are usually 2 and 3 times larger than if you come with a light like this. So these have to be taken into account. But the important part is that you have to check, mainly when you are comparing with experiment, what is done in the experiment. Because for instance, for the case that you are coming with an attosecond pulse, if you have a way in the experiment to measure what was the orientation of the molecule, for instance, this can be done with coincidence determinant with momentum coincidence detection, cold streams or even BMI, and you can see what was the light polarization with respect to the molecule, then you can see where, if you were in a specific case, so you have a fixed in space molecule. So if you are using very short pulses, for instance, you can know that this, you can ignore the rotation of the molecule in the simulation itself, But if you are considering, for instance, very long pulses, interaction with very long pulses, then I mean, it depends a lot on the experiment, on the observables you want to look at. I mean, but definitely the orientation of the molecule with respect to the light matters. I mean, it changes the results, definitely.
Thank you very much. Thank you.
So are there further questions, comments? If not, I'm going to stop the live streaming soon. We can continue the questions afterwards, but I would like to thank Dr. Palacios for the really nice talk and for agreeing. There's one. Okay.
Yeah.
Anonymous, in the CC and trajectories, you seem to get some very comparatively large bond lengths for a few trajectories. Is this an issue? If so, how do you deal with it?
You seem to get some very large bond lengths. No, not at all. I mean, the fact that in the dynamics you have very long bond lengths, that means that you are in your way to full fragmentation. So it's not a problem. Quite opposite. This is what your trajectories are giving. You mean theoretically speaking, in the sense that then it's a pain to represent the. You mean for the theoretical side, for the theoretical description of the wave function itself? Like when I do the electronic simulations, I guess. Yeah, I mean, if the anonymous can say, because, I mean, it's not a problem because that means this is my trajectories. I mean, they're separated and you represent it. So I don't see any, unless you mean it's a bit more painful and you have to be extra careful with the quantum chemistry package that you use. Because of course the representation of the neutral and the one in which you are here, you have to be careful to account for the proper basis. That, yes.
Would you like to clarify further, or that is fine with you?
Yeah.
Yeah, I don't know.
Okay. If I may, while talking, I found the figure I wanted to show to the person that asked about the effect of the electron leaving, because it was a very good question.
Okay, go ahead.
And I wanted to show the figure that I was trying to describe, okay? These are, for instance, okay, in this case, I'm just, this is glycine, okay? And these are the electron densities as a function of time. So what we are doing is, remember these densities that I was showing? So we integrate into the around different sites, no, in order to get, because this is very nice, but quantitatively it's difficult to compare. But in this figure, we are integrating over the different carbon, nitrogen, and the different oxygens. So we see the fluctuations, okay? And we are comparing in the full lines are the ones in which the n electrons are present. And the dashed lines are the electron densities in which we say, okay, we can ignore the electron that is gone. We just simply integrate over all of them and defines the density matrix, and that's it. And you can see the difference. As you can see, in half of femtosecond is exactly the same, okay? And you could say that around 200, 300, attoseconds, into 200, 300 attoseconds, it's totally fair to neglect it. So this is just to support that, because most of the works, you are right, we always ignore the electron in the continuum, and all the previous works have done it, but we check that it's actually a fair approximation. So I just wanted to show to the person who asked this. Sorry.
Thank you. I think it's really a very good point. So it's great that you had the opportunity.
Yeah.
Was a raised hand by Akanshka Dubey. Are you still around? Would you like to join? Not quite sure. Okay, I think we are good. So thank you for the nice talk. Yeah, I definitely agree. It was a great talk. We learned a lot.
Thank you.
Thank you for your talk. Thank you also for all of you watching. We had today over 90 people just joining, and we really appreciate the support that we are having from the Attosecond science community in these difficult times. It's really great to see that we keep on our discussions and our interactions despite of everything that is going on. So I'll stop the live stream and the recording. And if you would like to ask anything afterwards, which is off record, feel free to hang around or talk to our speaker. We'll have a few minutes. So thank you so much, YouTube people, for joining, and everybody else from wherever you're joining.
Thank you to everyone for attending.